Welcome to the deep dive. Today, we're trying to cut through some of the noise, both the optimism and the skepticism around energy. We're tackling that really pivotal question. Can renewables, like solar and wind, actually replace fossil fuels completely? Or is that, well, maybe more of a dream right now? We've looked at a whole range of sources. Some analyses project this amazing future where solar is like 90% cheaper, super exciting. But then you also get these surprisingly stark predictions. And they're coming straight from the big oil companies themselves. Yeah, the usual story is all about hope, right? You hear about the EV boom, see pictures of giant wind farms offshore. It feels like progress. But when you dig into the raw data, especially from major energy players, the picture gets, well, a lot messier, more complicated. And exploring that gap between the hope and this sort of logistical reality, that's our mission for this deep dive.
Exactly. And that logistical reality, that's where you find the curveball, right at the start. What's really fascinating, I think, is just understanding how incredibly sticky oil demand is. Take ExxonMobil, for instance. They've crunched the numbers, and they predict that even if, and this is a huge, if every single new passenger car sold worldwide by 2035 were electric, the world would still be consuming around 85 million barrels of oil per day by 2050.
85 million barrels. Wow. Just for context, isn't that roughly the same level the world was consuming back in like 2010?
Pretty much, yeah.
Yeah.
It fundamentally reframes the whole EV revolution, doesn't it? I mean, the EV boom is great. It tackles road transport, which is a big chunk of oil demand, definitely. But their projections show it barely makes a dent in the overall global consumption forecast. And BP, they're similarly cautious. Even with their big investments in renewables, they're still expecting demand around 75 million barrels per day by mid-century.
Okay. So our goal here is pretty clear then. We need to really understand why. Why is oil demand so stubborn? What are the key sectors relying on it that maybe we don't talk about as much? And crucially, what do the most viable long-term alternatives actually look like if we want genuine energy stability down the road?
All right, before we get bogged down in the challenges, let's just quickly lay the groundwork. Why is this transition considered mandatory, regardless of how hard it is?
Well, there are really two core reasons. You can't argue with them. First, obviously, is the climate crisis. Fossil fuels are the #1 driver of global warming. That's undeniable. The second reason is just geology. Fossil fuels are finite. They took hundreds of thousands, millions of years to form under immense natural pressure.
And the timeline for actually running out is kind of unnerving when you think about it. Estimates vary, naturally, depending on how much we use. But they suggest we could burn through the reserves we can actually get to, maybe in 50 to 150 years. That's not long-term planning. Not at all. And you contrast that with resources like wind, sun, geothermal heat. These rely on natural forces that are, well, constant, consistent. The sun's going to keep shining. The wind's going to keep blowing, right? So once you make that massive initial investment in the infrastructure, and it is massive renewables, promise a future-proof supply, you're not constantly hunting for more stuff to dig up from tricky places.
Okay, let's talk about the more immediate human side of things, too. Beyond just climate stability, what do the sources say about the sort of instant wins, the tangible benefits of switching?
Oh, the benefits are profound. And quick, you'd see a healthier, cleaner world almost immediately. The improved air quality, especially in cities. Dramatically fewer respiratory problems. That's huge for public health.
Plus, you reduce the risk of these awful environmental disasters like massive oil spills that just devastate ecosystems for decades.
Yeah, and we often forget the human cost for the workers, too. Coal mining, oil drilling, gas transport, these are inherently dangerous jobs. We still hear about tunnel collapses, fires, explosions, tragically often. Moving to alternatives absolutely reduces those dangerous work environments. And, maybe even more fundamentally, it addresses energy access. Over 1 billion people globally still don't have reliable electricity. Continuing to rely on an expensive, finite resource like oil, traded internationally, that's never going to solve the accessibility crisis for everyone. Plus, renewables tend to create more local jobs, often in rural areas where the wind farms or solar plants are actually built and operated. It boosts local economies.
Okay, so the case for transitioning seems, well, pretty overwhelming from that perspective. Necessary, even. But if it's so obvious, why isn't it happening faster? Which brings us back to that cold, hard reality check. The economics, the logistics, and why those big energy companies are predicting oil isn't going anywhere just yet.
Right. The core of the problem is that our public conversation tends to fixate on electric cars, almost exclusively. But road transport, that's just one slice of the pie. Big slice, sure, but still just a slice. We really need to look at what they call the hard-to-electrify sectors.
Okay, so what are we talking about there? What are the biggest energy users that are super difficult to switch over?
Aviation is the classic example. Think about a huge plane, like a Boeing 747. On a typical 10-hour flight across the Atlantic, it burns something like 30,000 gallons of jet fuel. The energy density needed is just enormous.
Right, you can't just strap a giant battery onto a 747.
Exactly. If you tried to power that flight with current battery tech, the batteries themselves would be so heavy the plane couldn't even take off. It's basic physics. And the same problem applies to those massive container ships crossing oceans. Just powering them with electricity is incredibly difficult right now.
And it's not just things that move, right? It's industry, too.
Big time. Heavy industries like making steel or cement, they require massive amounts of continuous heat, intense thermal energy. Electricity struggles to deliver that efficiently at scale currently. And then there's the big we often forget. Oil isn't just fuel. It's the fundamental building block, the feedstock for plastics, chemicals, fertilizers, pharmaceuticals, pretty much every manufactured thing we use.
Ah, right. So moving away from fossil fuels isn't just about changing what's in our gas tanks. It means completely rethinking entire industrial supply chains.
Entire industries, yeah. Not just swapping out gas stations for charging points.
Okay, then there's this other layer, the digital revolution paradox you mentioned earlier. We think of AI, cloud computing, all that digital stuff as clean, futuristic, but it uses a shocking amount of power.
Absolutely staggering amounts. Data centers. Their global power consumption is projected to jump by something like 160% by 2030.
Wow.
160%.
That new demand puts immense strain on the electricity grid. And today, that grid in most places still relies heavily on fossil fuels. Every time you do a search query, run an AI model, it burns power. And often, that power comes from coal or natural gas or oil.
So our fancy new digital world is actually driving up demand for old energy sources, compounding the problem. But even if we wanted to power all those new data centers cleanly, we hit the fundamental issue with the big renewables, don't we? Reliability, or what the industry calls intermittency. Exactly that. Reliability is the Achilles heel, the major structural challenge. Take solar farms. In North America, for example, they often only generate power about 20% of the time, averaged out.
Because the sun doesn't shine at night or when it's cloudy.
Right. And wind doesn't always blow consistently. You get lulls.
And this is why places like Germany, even though they've invested massively in renewables, they still need backup fossil fuel plants, right?
They absolutely do. They have to keep them on standby. They can't risk widespread blackouts if the weather changes unexpectedly, or if a high-pressure system parks itself over the country and the wind just stops for days.
And battery storage, while it's getting better and cheaper,
Yeah.
it's not there yet. Not enough to power whole cities through, say, a week of bad weather.
Not at that scale, no.
Okay.
Not yet. We're still a long way from having grid-scale storage that can handle long periods of low renewable generation reliably and affordably.
Okay. So given that intermittency challenge, it becomes clear pretty quickly that no single renewable source can just swap in for fossil fuels on its own.
No silver bullet. It has to be a combination, a diverse energy portfolio. You need a mix of alternative, tailored to what works best geographically and what meets different kinds of energy demand.
All right, let's talk about that portfolio then. If consistency is the biggest issue, maybe we should start with the option that offers the most reliable, consistent power. Nuclear. It runs all the time. Why aren't we just building nuclear plants everywhere?
Well, nuclear is the ultimate baseload power source. It runs 24/7, close to 100% capacity factor most of the time. In the U.S., it provides about 55% of all emission-free electricity. The big hurdles have always been, first, the enormous upfront cost of building those huge traditional plants, and second, public perception and safety concerns.
Right, the cost is billions, and people worry about accidents, even if they're rare.
Exactly. But there's interesting movement now. The U.S. and other countries are seriously exploring what are called small modular reactors, or SMRs.
SMRs, why are they potentially a game changer?
Well, the idea is they could tackle the cost and deployment problem. SMRs are designed to be much smaller, potentially factory-built, easier to transport and install. This could drastically lower that huge capital investment barrier that makes traditional nuclear so difficult. You look at France, they get around 70% of their electricity from nuclear. It shows it can be done at scale.
But the downsides don't disappear entirely with SMRs, do they?
No. You still have the political risk, the perceived risk of accidents, however small, and you still have the very real, very costly, and politically thorny issue of what to do with the toxic radioactive waste long term. That hasn't been solved.
Okay, shifting gears to the more common renewable solar and wind. They're getting cheaper, they're abundant, But they introduce a different kind of dependency, don't they? It's not just engineering, it's geopolitics.
That's a really crucial point. The energy transition isn't eliminating resource dependency, it's shifting it.
Mm.
Instead of relying on certain regions for oil and gas, we become heavily reliant on other regions for the critical minerals needed for batteries, solar panels, wind turbines.
Things like lithium, cobalt, rare earth metals.
Exactly. And the mining and processing for those are concentrated in just a few countries. This creates completely new global supply chain risks, new potential choke points, new geopolitical leverage. Energy policymakers have a whole new set of dependencies to manage.
Okay, let's quickly round out the other key players in this potential future energy mix. There's hydropower. Right?
Hydro, it's clean, uses natural water flow to very established technology, often multi-purpose, helping with flood control and irrigation too. Reliable, where you have the water resources.
And wind energy.
Wind is great. An average wind project actually pays back the carbon emissions from its manufacturing and installation in less than 6 months, which is incredibly fast. It uses an infinite resource, generates no waste during operation. Especially effective in remote areas or offshore, though maybe not ideal right in cities.
Then solar, you mentioned it's getting cheaper.
Incredibly versatile. Clean, obviously. And it's unique because it's accessible to individuals. You can put panels on your own roof. Getting better in low light too, but still weather dependent, and panels do degrade over time.
Now, before we wrap up the alternatives, there's one that often gets lumped in with renewables, but you mentioned it needs a careful distinction: biomass.
Yes, this is vital to clarify. Biomass is renewable, technically. It comes from things like wood, plants, animal waste, stuff we can grow more of. But, and this is the key point, it is not considered a truly clean energy source in the same way as wind or solar.
Because burning it still releases carbon.
Exactly. Burning wood or biofuels still releases CO2 into the atmosphere. So while it can reduce reliance on fossil fuels, it's not zero emission. It's an important distinction.
Okay. And any other up-and-comers to watch?
Definitely keep an eye on tidal energy. It's newer, but showing real promise, especially in coastal areas with strong tides, like the UK. One study suggested tidal could potentially meet almost 20% of the UK's electricity demand someday. And the big advantage is predictability. Tides are very regular.
Okay, so we have this complex portfolio of options. But putting it all together, what's the real cost of making this massive shift happen? You mentioned infrastructure earlier. It sounds like the biggest long-term cost isn't just buying new tech, but ripping out and replacing the old systems.
That's a huge part of it, yes. Our entire energy infrastructure, the grid, pipelines, distribution networks, everything was designed and built over a century. Fundamentally around centralized fossil fuel power plants, changing that to accommodate distributed intermittent renewables, plus potentially more nuclear or hydro. That's a monumental engineering and financial undertaking, an overhaul.
And that overhaul has real economic consequences for people and businesses, right?
Absolutely. Businesses built around the old system will have to adapt or disappear. That inevitably means job losses in some traditional sectors, even while many new jobs are created in clean energy manufacturing, installation, maintenance. Change is disruptive, it's costly, and it takes time. Often, frankly, more time than the climate science says we have.
And meanwhile, we still need to keep the lights on using the current system. You mentioned that ExxonMobil warning.
Yeah, they caution that if investment in existing oil and gas production drops off too quickly before the alternatives are truly ready at scale, global supply could potentially fall sharply, maybe by 15 million barrels per day within just a year or so.
Which would cause prices to
What?
skyrocket.
Exactly, potentially sending oil prices soaring by 2030. Just finding and developing new oil sources to maintain current supply is already getting much more expensive. Exploration costs are doubling in some cases.
So putting all this analysis together, what's the general consensus? Is the transition possible? And what does the timeline realistically look like?
The consensus seems pretty clear, if maybe a bit sobering. Yes, the transition is possible. Technically, economically, it can be done. But it requires absolutely massive initial investment. And crucially, it requires dual investment for a period.
Meaning investing in the new clean stuff and still investing enough in the old fossil fuel system to ensure stability during the changeover.
Precisely. You can't just switch off the old system overnight. So it requires huge capital for renewables, nuclear grid upgrades, and continued investment to prevent destabilizing shocks in the existing oil and gas supply. And because of that scale and complexity, this process won't be fast. We're likely talking 4 or 5 decades, 40 or 50 years, before the energy mix truly shifts in a way that's globally recognizable and stable.
So the future isn't purely renewable anytime soon. It's a carefully managed mix.
It has to be. A thoroughly planned, optimized mix, using oil where it's still necessary or hard to replace, ramping up renewables massively, incorporating nuclear for baseload, using hydro where feasible, each source playing to its strengths.
Okay, so the core takeaway for your listening is probably this. The immediate race isn't about eliminating oil entirely tomorrow. That's not realistic according to these analyses. It's really about fundamentally shifting the balance of that energy mix over decades. And critically, building the modern, resilient, probably more decentralized infrastructure that can actually handle power reliably from all these diverse sources.
And thinking about that long transition and the dual investment needed, it raises a really important, maybe provocative final question for you to consider. We know fossil fuels are finite and cause climate change. We also know renewables, right now, have intermittency issues needing backup or storage that isn't fully there yet. So if the cost of not investing enough in new oil supply now is potentially skyrocketing energy prices and instability in the near term, and the cost of not investing enough in renewables in the new grid now is climate disaster and a much harder, costlier transition later. How should we, or how should policymakers, prioritize that critical initial investment money, especially when the full transition might take half a century to really bed in? Faced with those two competing risks, short-term price shocks versus long-term climate and infrastructure challenges, which investment path actually guarantees the most stable, reliable energy supply for you over, say, the next 20 years?
It's a tough balancing act, a really complicated question for a very complex global energy system that's in flux. Thanks for diving deep with us today. Hopefully, this gives you a clearer picture of just how intricate this global energy shift really is.